So much for being here for our first IU lunch talk of 2019. So we're really excited to have Elena Kulinskaya, who is a professor of statistics at the University of East Anglia, as our first speaker for 2019. Before I start, for all of you who don't know, the IU, or the Independent Evaluation Unit, hosts monthly lunch talks to showcase experts and leaders in the space of development, climate change, methodological thinking, and technical advice, so that we can raise the standard of how we ourselves at GCF are collectively thinking about policies, strategies, and our investments. In keeping with this, we invite leaders from around the world to come and speak to us and to engage with us. Previously, we've had experts and leaders come from diverse international as well as national agencies that have worked on a diverse set of issues related, for example, to machine learning, to measuring results at the Global Environment Facility, to looking at how to use GIS, for example, in measuring for results, etc. Like I said, these lunch talks are held every month. We invite all of you to also give us suggestions on who you'd like to see invited and who you'd like to see featured at these lunch talks. They are open to everyone and anyone, and these are not just GCF or UN specific lunch talks. We invite everyone to come and cross-fertilize their ideas with us. We use these as fora where we can piggyback on ideas that are coming from the rest of the world, and we expect you to do the same. Before I go forward, just the lay of the land and how this will proceed. While all of you eat your lunches, we'll have Elena speak for about 20 to 25 minutes. I know the topic today is somewhat, technical, given its statistical nature, but what I'm going to encourage you to do, with your permission, Elena, is to also ask clarificatory questions during the talk. So we're all sitting in a nice space here. Please do ask clarificatory questions. We can have the more, theoretical, discussion-oriented questions at the end, but definitely clarificatory things that you don't understand. Use this time to really raise the bar that you've come in with, and to raise our bar, because remember, if you have a question, it means at least 50% of the audience has a question. Yeah. I'm also going to encourage you to tweet this talk if you can. Our handle and our hashtag is on the screen. And subsequently, if you have ideas on others that we might feature, please let us know as well. Before I hand this over to Elena, our next month's talks will piggyback on the board meeting that will be hosted at GCF, so at B22. We will have 2 or 3 talks, actually, that will be side events to B22, and we'll be showcasing those, and those will be open to everyone as well. So just to put that on your radar. For now, if this is without interruption, Elena will speak for about 25 minutes, but definitely don't hold back on clarifications, and we'll go up till about 1:30. So with that, welcome, Elena, and over to you.
Thank you very much, and thanks very much for inviting me to this beautiful country. It's the first time I go to South Korea, and of course it's partly due to this invitation to give a talk, so I'm really excited about it, and I've seen lots of interesting things already. And of course it's a privilege to talk to such a high body of people, and I hope that this talk won't be very technical. I tried to eliminate all formula from it. I promise there won't be one formula in the talk. There will be some pictures. Okay, but yes, as Joe said, don't hesitate to ask questions to understand what this is about. Okay,
Page down.
Oh, page down, okay. Oh, no, I want a full screen.
Yeah, she'll do it.
but will it...
Yeah.
No, you have to...
What? I need to scroll.
Okay.
No, it will. You just press page down.
Sure?
Yeah.
Because I don't like it. It's kind of...
Yeah.
Okay, fine. Okay, right. We'll see how it goes. So as you see, I'm going to talk today about temporal trends in effect sizes, causes, detection, and policy implications of them. This is a very quick summary. Contents of my talk, I won't dwell on it. It will be 4 sections. Right. So I'm also here for the last 2 days to do a course on meta-analysis. And of course, meta-analysis is a part of systematic review. So if we want an evidence-based policy, we should do systematic reviews of current experience to understand what actually is going on. And general aim of meta-analysis is to combine scientific evidence to create generalizations and provide the evidence base for decision making in various scientific fields. Sorry, it doesn't work. I need to scroll. Okay. Oh, it does? Because I made pause. Oh, okay, right, I see. However, scientific evidence, it's okay, I will do it myself. Scientific evidence is not static and it may evolve with time. So any given systematic review and meta-analysis provides just a snapshot of the evidence at more or less arbitrary point in time where we have done that meta-analysis. And things may change. So new studies may either straighten or more often challenge the conclusions of previous reports. And we'll see the examples of that further in this talk. This is a very nice article in New Yorker back from 2008 by John Elera, which was on this topic. And it was a very nice, passionate article, which I really recommend you to read. It starts from a problem which appeared in the field of psychiatry, where they had a particular, rather new kind of antipsychotic drugs, which worked much, much better than traditional drugs for this problem. And everything went smashing, and then suddenly effect of these new drugs seemed to disappear, and at the end they were not performing any better, or even sometimes worse than the traditional drugs. And this is how this article starts. And then it goes on to give other very striking examples of this change in effect sizes over time in various areas of science, including medicine, but including, say, ecology and evolutionary biology as well. So this is the problem we are going to talk about today. So basically, what this endangers is the replication validity of science, because we expect that when we repeat our experiment many times, we are going to get more or less the same answer, which doesn't shift when we add additional data. And we assume that this accumulation of replicated effects should converge somewhere towards the truth. So if the reported effect size changes over time, then this kind of endangers a replication validity of our science. So this is really kind of a very important problem for the development of science. As I said, temporal changes in effect sizes have been reported in many scientific fields, including medicine, social sciences, ecology, and evolutionary biology. It usually goes that they go down. the earlier studies would give a larger estimate of effect than subsequent studies. Sometimes I have seen reports of things going up, but it, on average, happens much more rarely than effects diminishing over time. And this is just one example. This is a very nice handbook on meta-analysis in ecology and evolution. I think Oxford University Press 2013, and there they have special chapter 15 on temporal trends in effects. And there they provide a list of 18 meta-analyses which tested for temporal changes in effect sizes, and only one reported increase in effect size, 3 reported no changes, and 14 reported decrease in effects over time. So overall, majority of meta-analysis seem to show diminishing effects over time.
How many know what an effect size is?
I should just say effects, really. Yeah. We find an effect of some intervention, whatever it is, whether of conservation, of a management intervention, or of medical intervention, and that effect seems to disappear over time, so that the drug was much better than another drug to start with, and then it becomes no different. Conservation measures seem to be much better than no conservation, and then suddenly we don't see any effect. This kind of thing. Okay? This is the same article, which I quite like because he has this very dramatic style. So I will read the first para from it. It says, but now all sorts of well-established, multiply confirmed findings have started to look increasingly uncertain. It's as if our effects were losing their truth. Claims that have been enshrined in textbooks are suddenly unprovable. This phenomenon doesn't yet have an official name. I'll stop here because now this phenomenon does have an official name. And the name of this phenomenon is the decline effect. So the decline effect is the notion that reported effect sizes can diminish in magnitude over time. Effects, I shouldn't say effect sizes. Partly it is due to the well-known fact that the larger you have a study, the smaller sometimes is an effect they report. It has to do, to a large extent, with publication biases, because usually at first you get a pretty small studies who publish some dramatic new finding, and everyone is very excited about it, but when you do really large trial, you see that it was just a fluke. Nothing really happened. So this is just kind of publication bias kind of effects. There is another very similar effect, which is called the Proteus phenomenon. And that Proteus name, of course, comes from the Greek myth, and it is due to John Ioannidis, who came up with this nice name. So in the Proteus phenomenon, the first published study usually has an outstanding, really large effect. And then someone else repeats the study, and they found completely opposite effect, also large, but kind of in opposite direction. So once more, very contradictory result. And of course, editors love controversy. So both papers are published with a lot of kind of coverage and all that. And then there are lots and lots of other studies because everyone wants to see what's going on, and they show kind of very average, diminishing, nothing much interesting effects. So this is called Proteus phenomenon. And of course, it's also kind of result of various biases because of this love of controversy, this and that. So this is not real kind of temporal change. This is just some random flukes due to psychology and biases and this kind of thing. So here, just because, as I said, journals love to have impressive findings. Okay, this is a real example, which doesn't have to do with Proteus phenomenon, but it is an example of actual temporal changes within systematic reviews. The first meta-analysis by Cotter and Sutherland was done in 1997, and that combined evidence on effects of predator removal on bird populations. And the results showed that predator removal significantly increases post-breeding population. That means there are a lot of birds in the autumn, but doesn't significantly affect breeding population sizes. So they came up with a conclusion that the predator removal fulfills the goal of game management, but is of less use for conservation management. Okay, everyone believed them, time went on, and then in 13 years, a meta-analysis on the same topic by Smith et al. Arrived at completely opposite conclusions. They found that the predator removal effect on breeding populations was statistically significant, but the magnitude of the effect on post-breeding populations was 3.7 times lower than before and was no longer significant. So they came with opposite conclusions that predator removal is an effective strategy for conservation of bird populations, but not for game management. So we have two meta-analyses, two systematic reviews, same topic, opposite conclusions, implications for conservation and management. Okay, why? These are the results. The white are the first one, and the gray are the second systematic review. So here you can see that there is strong effect on post-breeding populations in the first review, but not in the second. And here you see strong effect in the second review, but not in the first. That's how they look like.
What's the post-breeding population?
After they had their children, and yeah, so now after post-breeding you have much more young birds in the autumn.
But they don't have to breed.
Well, they do breed.
Yeah.
We removed predators, and we look how it changed number of birds, how it changes breeding patterns, whether they have more children, more eggs, I would say, more young birds survive, so breeding. And then we look in the autumn how many are there after this summer cycle of breeding. Okay?
Thank you.
So anyway, two opposite effects. Why? Any suggestions? Okay, actually, in this case, I'll actually tell you later. I'll first tell you what reasons there may be. So I'll tell you after one slide, in between, what was the reason, okay? What I wanted to say is, okay, that was an example of importance of changes. Now, example of importance of no changes. This is why a lack of temporal change also is very important to know. Basically, if we are expecting changes in effectiveness, then lack of changes is very important thing to know. Like we expect that we are investing money into something, into some policy, we expect it will change something, and it doesn't. Good to know, isn't it? And this is example of exactly that. Maybe this one will be closer to home. So, for instance, there are so-called agri-environment environmental schemes, AES, in Europe, which are used for about 25 years and are the biggest conservation expenditure in Europe. And national AES programs are revised every 7 years. So the last one was revised in 2007. And then there was meta-analysis by Battery and others. So it was 8 years after the change of policy in 2007. And they showed that the effectiveness of these schemes has not changed as a result of this revision of policy. No change whatsoever. And this is really worrying because they were going to revise it once more. And they were going to cut some money from that program. And if it didn't work before, it certainly won't work any better if they cut the money. So it's important to know that something doesn't bring any changes. So basically, it is important to look whether there are changes and make appropriate conclusions, either that yes, there are changes or there are no changes. Okay, so far? Okay, now I will open you that secret about why the previous two systematic reviews had opposite conclusions. And that is due to heterogeneity, which is one of the very important causes of temporal changes. So in the first review, they looked at a population in the mainland. And then in the second meta-analysis, they were adding more data for islands. And because they were looking at different populations, they were finding on average different effects. So this shows that it's very, very important to look at how heterogeneous are the studies you're trying to put together. And only because the studies kind of change location, you get opposite results. Okay, so this is the first reason for temporal changes. Just your population is changes. What you're doing is not quite what you think you were doing before. Okay? The second reason for temporal changes is biases, and I put here just 5 possible biases, but in fact there may be much more different biases, which may be a reason for seeming changes. There may be publication bias. At first they only publish significant results, but over time they start publishing all results, so your significance disappears over time. There may be a time lag, so first they publish the most striking results, and then they start publishing some not so striking results. There can be different study organisms, there can be paradigm shifts, there may be some different statistical methods. So all these are different biases. And of course, if there are biases, we shouldn't worry too much, because really nothing changes, but we should once more notice it, and we should try to adjust for those biases if we want to know the true effect. So we need to use perhaps some statistical methods to adjust for those biases. Okay. This is the most important reason for temporal changes, and this is true changes, which also do happen. As you especially should know, say changes due to climate change, for instance, because there may be changes due to relevant changes in the strength and relative importance of the drivers of biodiversity loss and to rapid adaptive evolution. And those are kind of real changes. And you need to notice and incorporate this knowledge into your policies, really. So if true biological effects are changing over time, then you need to take some action to reevaluate conservation status and strategy for a given species or some environmental management options. Yeah.
Sorry. Just one question. You shown biases, and one of which was paradigm shift, and I know my fellow colleagues will know that even better. Paradigm shift is a big question here, or a big discussion here at the GCF. So I was just wondering, is a true effect the paradigm shift you're talking about, or how would I understand the bias and paradigm shift?
Paradigm shift would change publication strategies. So people who were publishing one thing, now the crowd is publishing something different. So it will change your meta-analysis because once more incorporating different things in, but also, of course, it will change true effects. Yeah. I mean, fashionable things, it's, yeah, whatever it is, bias, I suppose, yeah. Okay, but
Yes, I just want to follow up on this question because in your case, and it's well understood, you have shown how paradigm shift can change effects in the effect. But in our case, what we usually try to do is to justify paradigm shift through our analysis, how we can do any kind of analysis to demonstrate that we will achieve paradigm shift at the end. I think is the way I see the difference, and maybe at the end of your presentation, I will come back with more precisely how we can apply this to adaptation to climate change stuff.
okay, so first you need to notice the shift. Then you need to explain it. And then you need to think what to do about it, yes. They are kind of different steps. But we will talk a little bit more about it. Yeah. So first of all, we need to detect temporal change. So this is what I move it to. After we detect it, we can think why. Okay. So the first way to detect temporal shifts were to do with simple regression and correlation approaches. So it's very simple. You just take correlation of your effects with time of publication. You do correlation, or you do just simple regression with time, and you see whether it looks like there is this correlation. And if there is correlation, means there is trend over time. But of course, here we're talking only about linear trend. So, for example, this is an example of ecological meta-analysis. I thought I'm dealing with ecologists here. I was wrong. Meta-analysis on herbivory and mycorrhiza. And here you can see straight away in this first picture, this is year of publication, and this is the effect, the difference between control and treatment, say. And you can see pretty clear linear effect over time, like your line here is going up, and time explains 20%, 21% of all variation in your effects. Okay? So it's easy to notice this kind of thing. Of course, it only works with linear changes. So if something has a more complicated pattern, this method won't work. But there are other methods. For example, this one is a very nice visual method, which is called Cumulative Meta-Analysis. And this is also very simple. So what we do here, we have the effects from different studies, and we order them in the order of publication, say. And when we do system meta-analysis, we first pull first and the second together. Then we pull first, second, and third together. Then we pull all four together, and we see how the summary effect changes over time. And the advantage here would be that you can see not only linear effects, but you can see how lines they goes down and goes up again. So this is an example of this one. So, yeah.
In your previous example, Elena, the slide before this one, so there's no decline effect?
No, there are no decline effect here, but
Because
there
the
is-
effect sizes are increasing, actually.
Yes, I told you that sometimes they go up.
Yeah.
They not always go down. In majority of examples, I know they go down, but sometimes opposite happens. Yes.
And the example on the right, the chart on the right?
That they try to see whether there was correlation with the duration of the study, and here
Got it.
the answer is no, really. Yeah.
Okay. Duration of the study.
Yeah.
Okay, yeah, got it. Thank you.
Okay, so this is an example of cumulative meta-analysis. So here the hypothesis was that some endophytic fungi in grasses act as plant mutualists and protect the plants from herbivores. And this was meta-analysis of 47 studies which continued for 20 years, from 85 to 2005, so quite a long time. And this is our effect is correlation between the degree of endophytic infection in grasses and plant resistance to herbivores. So positive correlation supports the hypothesis in this meta-analysis. So you can see we started with pretty high effect, then probably the second study had lower effect, so combined effect was lower and not significant anymore. It had continued being non-significant for quite a while. Then here it became significant for about 3 publications, and then it stopped being significant and continued like that, more or less, on the same place for the rest of these 20 years. So here effect was first high and then it goes down. But this is not the only pattern possible. So if you look at this quite interesting paper by Foncho and others about the medical meta-analysis in the Cochrane Library, they looked at almost 1,300 of medical meta-analysis, and they identified 5 different patterns. So you can see that in 33%, the significant effect was never reached. Only at the end, effect was reached in 2.5% of meta-analysis. Significant effect was retained in 39% only of meta-analysis. Here, first you get significance, and then it disappears, and it disappears forever. And this one is lost significance, and then it returns to significance after a while. And that happens in 13%. But I think that this is really quite striking number, like only in 39% of the systematic reviews, your significant effect stays always significant. In other cases, things may change over time. Okay? As all visual tools, cumulative meta-analysis is very nice, but it may be misinterpreted, and it is to do with so-called issue of multiple comparisons, multiple testing, because every time after every publication we test the same hypothesis once more. Is it significant, is it not? So we repeat the same test, 40, 50 times, and we might get significance just by chance. So there are statistical methods which try to cope with this problem, and the majority of these methods try to borrow methods which are already developed for sequential clinical trials. So sequential clinical trials plan that we would have, say, 5 stages. After each stage, we would test whether we've got a better treatment, and if at some stage we do, or other way around, we don't at all, we stop, because it's unethical to continue with this trial. And there are a lot of publications about this, but So basically what they do, they have kind of boundaries which look like this, and every time you test, when you cross a boundary, you stop. This is called trial sequential analysis, but this analogy with sequential trial is completely wrong for meta-analysis, because you can't just stop meta-analysis, because what other people publish, you can't tell them, just stop, we already know the answer. So they will continue regardless. So it's not quite what we do in meta-analysis. So this is not quite working, even though this method, this group was very kind of pushy and tried to incorporate it into Cochrane methodology, but it didn't work. What we also thought would be reasonable to do is to look at the so-called quality control charts which are used in industry to see whether the process of production is under control. And there are two kinds of quality control charts we can use here. One is called X-bar chart, and one is called Q-sub chart. So for X-bar chart, you kind of see whether there are some outlier studies. I'll show you a picture in a moment. And for Q-sub charts, you look at a cumulative sum of deviations. And it's easy to see change when your deviation kind of accumulates over time. So just show you one picture. We're talking about exactly the same meta-analysis you have seen already before of Seikonin and others, and that was the cumulative meta-analysis which you have seen before. But now the second chart here is the X-bar chart. You can see the first study is an outlier, this study is an outlier, this study perhaps also an outlier, but at a low, down to low. And this is a Q-sub chart, so here you can see that by this point we can see that your trend went up too much. It's significant. So now I'm coming to the final summary, two stages in the accumulation of evidence. So a first stage is a setup. Sequential methods of meta-analysis can be used to establish significance and stability of the accumulated evidence. So we say, now this effect is significant, it seems to be stabilized. What do we do now? Now we need to monitor it. And that would be the second stage. So we are checking whether there are any temporal changes in it over time. And we could use those Q-sub charts to see whether the effect is still where it was. Then, if we do notice a change, we need to decide what's going on. What is the cause of this change? Is it biases? Is it heterogeneity? If it's biases, we need to adjust for those biases to see what is the true effect. And if it's heterogeneity, we need to find the moderators and try to understand what's going on, what works where. And finally, if we do have an actual rapid temporal change in true biological effect, then it should inform our decision making on whether these changes require adjustment in previously accepted policies. So that's it. I'm finished. I hope in time. Thank you.
Thank you so much, Elena. Very interesting.
I hope it wasn't very technical.
No, I loved your examples, actually. Yeah, very interesting, and especially because I come from a resource economics background. For me, it was really interesting to see some of the more ecological ecosystems examples and to think a little bit out of the box as well. Okay, this is that bewitching hour where you all get to ask questions and to talk about some of the things that you've learned. Please raise your hands. We'll take about 2 to 3 questions in one lot and then get Elena to also discuss them with you. Sandra, go for it.
Thank you very much. It's very interesting. I think I would like to know if you have been able to have some interest in the same application for biophysical science, especially for climate change, and just to give us illustration how the process work to show detection and action and attribution to climate change. That will be very interesting for us, because the challenge we have, especially when we have to deal with adaptation, whenever we encourage stakeholder, project developer countries to use some of these methods to be able to provide scientific evidence for the risk, and also for the prioritization of adaptation that will likely address those risks. They are reluctant. They will refer to issues related to data, the issue related to the capacity to use some methods to prove anything, and then we will just be in this world of uncertainty where we really don't know what we are dealing with and what we are finding. It's really adaptation. If these things can help in the future, so we just want to better understand the challenge and how we can also help our stakeholder improve those methods to be able to apply them if possible.
Thank you very much.
Mike.
Okay. Thank you very much. It's a very important and very interesting question. I have to say that I don't know that much about findings for climate change specifically. I think I've seen several papers which are talking about changes in reefs across the world, like Great Barrier Reef and that kind of thing. And I've seen once more systematic reviews at an older stage and recent ones, and they seem to show that there are quite a bit of adaptation-related changes in this area. But I'm afraid that I can't give you more examples. Of course, we know very well other examples of real biological changes. Take, for example, antibiotic resistance. It's one of the main problems in medicine these days, which is also kind of endangers mankind. And this is exactly an example where, due to adaptation to antibiotics in this instance, effects disappeared. And we need to do something very quickly about it. We need to change all our prescription policies and so on and so on. So this is also quite relevant example of this pretty global changes, if you want. How to find them? Well, sometimes you see, like with antibiotic resistance, it's pretty easy to notice, but sometimes, of course, you do need to monitor effects. So you are just starting doing systematic reviews. I hope when you continue more than 1 year, because you don't have much time scope, it is useful to monitor results, because, as I said, if you notice a change, it tells you something, but also if you see that things don't change, it also tells you something. For example, it tells you how successful are your policies if you put more and more money and you don't get any changes. Maybe you don't need to put that much money into it, and the other way around, okay? I don't think you want me to tell you statistical methods how to change the cases, but visually you can do this cumulative meta-analysis, and you actually have a command in Metaphor, which I'm teaching quite few of you now to do this first method, to do cumulative meta-analysis. So at least by eye, you can see where the things are going somewhere in some direction. I can very quickly show you how to do it later in Metaphor.
So, sorry, Sandra, just to add that Elena is referring to the training that the IU team is going through. And if you, so they've been in training yesterday and today, and the data lab especially. So if you have questions related to this, about how to do it, you're training them sufficiently that they can answer
I'm
these
sure
questions.
they can do at least cumulative meta-analysis. It's easy.
Yeah.
Then my follow-up question from your fields will be if you can explain to us what have been the process to to translate scientific information and apply them to policy, because you did give evidence in your presentation on your field. So what have been the process? Because sometimes you have two different worlds, right? You have those doing the science, you have those policymakers, and sometimes you might need interface to be able to translate. So what have been the process in your field that help to make sure that information that came from science become usable for policy and decision making?
I prefer to stick to example of antibiotic resistances, because, as you may know, antibiotic resistance appeared because in many countries people were prescribed antibiotics without any discrimination, if you want, to the causes of the disease. So they were prescribed for viral infections as well as for bacterial infections. And in the result, when antibiotics don't help, at the same time, bacteria develop adaptation, develop resistance to antibiotics. So that really overprescription was the reason for antibiotic resistance. And that changed quite a lot of prescription policies, for example, in the United Kingdom, where I work. So now, for example, when you go to your primary care practitioner, to the GP, in general practitioner in British terminology, they would think before they prescribe you antibiotics. If you just have sore throat, for example, they will say it's a viral infection. We won't prescribe you antibiotics, okay? Because they know that the less they prescribe, the better it is for the general population, because it doesn't develop this extra resistance. So prescription policies and the length of time they prescribe antibiotics, and that all changed exactly to try to cope with this issue. I don't know whether this is I think it's a relevant example.
Thanks, Elena. Drazen.
It's actually Dražen, not Dražen, but okay. Очень приятно.
I will never learn.
So we are essentially bankers for climate, and I would like to go back to the question of biases. The climate change is externality that really is trying to avoid path dependency on fossil fuels and all other sustainable forms of human forms that are leading us to a disaster, yeah? So paradigm shift, in fact, the one that you mentioned, is actually an investment criteria. We have 6 investment criteria. One of them is paradigm shift. So we are trying to avoid the path dependency. We have a significant externality, which is being boosted all the time by the growing humanity, yeah? And then we say we have a paradigm shift, and we instigate a paradigm shift, which on its own can be a bias. So how do we in our investment decisions and investment policies, how do we recognize biases?
Sorry, can you give me an example of a paradigm shift? Because
Sure.
I'm not sure about your terminology.
Okay, paradigm shift. Okay, I'll give you a real life example. Paradigm shift is, for instance, when we intervene in Solomon Islands. Population there has been using diesel fuel oils for 100% of energy related sources. Now, when we intervene and we create alternative energy sources such as hydropower, we reduce the diesel usage to about 60 to 80% permanently. So that's a paradigm shift. So we move from unsustainable sources of energy to sustainable sources of energy. That would be a paradigm shift. So we have a path dependencies all the time. We are fighting path dependency which trying to instigate paradigm shift against the externality, which is a climate change. But then, obviously, we have to be phenomenally aware of biases in our investment decisions. And I think that's something I would like to pick up from your presentation. How do we fight biases?
Okay. I think it very much depends, first of all, at what effects you are looking at, because there may be multitude of effects due to this particular paradigm shift. For example, talking about even this example, you change mode of heating. This change may change by 1 degree or by 2 degrees temperature within dwellings, for instance. This may have various effects. For example, it may have, of course, saving energy effects, but it also may have good or bad, I have no idea which, health effects. So the question is, what effects are we talking about, first of all, before we decide how this paradigm shift affects various things. So if we just look at use of energy, I suppose we see straight away that overall effect goes down. When we look at health effect, we probably need much longer time span to see what was the effect on that, and so on. So it's not that straightforward, really.
Sorry, may I come in? Actually, Drazen. So in our, as we've been thinking about paradigm shift, there are a few attributes of paradigm shift that we've considered at the IEU. One of them is exactly the sort of change that you've talked about. And in Elena's language, it's basically saying that there are large effect sizes. Yeah? So the 100 to 80% or 100 to 60% would be a large effect.
It is pretty large effect,
yeah?
Yes.
So one is that we think that it should be associated with a large effect. But we're also saying a couple of other things. First, that although that effect may be large, so there is depth in that effect, it should be large scale as well. So it shouldn't just be one community on the Solomon Islands, it should be for all of Solomon Islands, right? So it should be at a large scale. The third is that it should be sustained over time. So it shouldn't be evanescent or fleeting. It should stay for a certain period of time so that it stays there. And last but not least, if it requires behavior change in the last mile, that's also there. Yeah. So because that's what is going to ultimately lead to is going to be sustained over long periods of time. So if it requires that households in the Solomon Islands are changing their behavior and moving towards renewables, then we should be able to detect that at a large enough level. Those are 4 attributes that we think are necessary, but clearly not sufficient. I can think of at least 5 other attributes that you should be able to associate with paradigm shift and or transformational change that you should be able to pick up. But those change according to context. But these 4 things, I think, are pretty clearly associated with something that is large, sustained, large scale, and will lead to systems change. Given that, I think your question becomes really interesting, primarily because paradigm shift might be, in a mathematical equation, it would be called a state variable, right? So it's basically something that's going to be the shift in my variable. But according to what you're also presenting, Elena, the way we have to think about it is that in itself, it might induce a bias in the effect, in the impact that we are seeing. So I think we need to marry, what Drazen is asking with how you're stating that paradigm shift might be a shift variable or something that might induce a bias.
I think that it may be to do also with terminology, what exactly is the paradigm shift. That's why I asked, because from your point of view, paradigm shift is that more people now are using organic whatever, or they stopped eating meat, like in British papers I read just yesterday that we all should eat hamburger once a month if we want to, whatever.
Okay. Any comments on eating hamburgers once a month, Joseph?
I have to say that I have no idea what health effects that would give, so we'll see.
So it's the ecosystem effect, of course, as we know. Meat has far wider ecosystem effects than vegetables do.
Yeah, I understand why.
Any other questions that are burning, etc.? Yes, Andres?
No, maybe only a comment.
Yeah.
So one comment is, Drazen, if you're really interested, what Joe has just referred to is also in writing on our IEU webpage. So there's papers on transformational change and we see it at the moment and how we'd like to look at it. That could be interesting. And to the question that Sandra raised, this is, so basically to give you background, this is exactly why Elena and Alexandra are here today. They've given us training on how to run meta-analysis as a part of systematic reviews. Because indeed we do look at that question, because we have currently 2 works that look at evidence gap maps. So that would be an instrument that tries to look at publication and what the publications tell us about climate change adaptation, as well as grey literature, which refers to a more practical impact assessments in a more practical sense, with a little bit more connection to what we know from the practice on the ground. So those are products that will be coming forward this year as well, just to let you know.
That's excellent, actually, Andreas. Thanks for reminding everyone that. So we will be looking at all of the evidence in adaptation that has ever been done in developing countries, ever, right? And that will be coming as a product very soon from the IU. And then we are doing similar work looking at the evidence related to effectiveness of forestry interventions, forestry-related interventions. That will also be coming out later this year. And also on transformational change and paradigm shift. So that's a multidisciplinary, we're looking at initiatives across energy, agriculture, disaster risk reduction, as well as in public health. So, so that we can learn, and we shouldn't be navel gazing. So as an institution, we should be able to learn from what is paradigm shifting in other disciplines. So we're going to bring that out this year as well. So we're hoping very much, of course, that you'll stay engaged with this conversation and dialogue. But with that, Elena, thank you so very much. I really loved your examples and really helped me to think about so many other things that we're doing. But it's, contributing really to making us practitioners think about what is academics telling us, so that we can really mediate and broker and bring in that knowledge into our own practices as well. With that, thank you very much, ladies and gentlemen. We look forward to staying in touch. Thank you.